I'd like to say that today's talk, Manuel is coming to us from Perth. He works for REE as a consultant now, but started his career in Germany. So he's doing his specialist master's degree, and then came to Australia in 2018 to do his PhD at Murdoch University of CSIRO. In 2021, he started with REE Consultants as well. Is that right, Manuel?
That is correct, yeah.
Great. And we'll just having a quick chat before. Apparently coming to Australia, Manuel's had a really crash course in regolith. So coming from a land of not much regolith, it's going to be great to hear about sort of what we take for granted, probably through a fresh lens and fresh eyes, fresh set pair of eyes, I suppose, when we comes to understanding rare earth elements in Australia and especially clay hosted. So it's going to be a really great talk. So what I might do, I'll stop waffling and I'll hand over to Manuel. So thank you very much for presenting.
Right, thanks for the kind introduction, Anna. Yeah, I came here as a hard rock geologist. I think he was a hard rock geologist, but then I had to learn a lot about regolith when I came over here to Australia. All right, let's talk a bit about rare earth. And yeah, I'm going to talk a bit about the work that we've done here at REE together with Nishka, Michael, Kat, Mohammed, and Madeline. And yeah, let's get into it. So what are clay-hosted rare earth? Timer again. Yeah. What are clay-hosted rare earth deposits? So they normally form when underlying granitic bedrock is being weathered, and your normal granitic bedrock has around 180 to 200 ppm TREO. That would be the sum of all the rare earth oxides together. Some more mineralized granites can have maybe up to 500 ppm TREO. And when that granite is weathered, what's left in the end is just halloysite and kaolinite and maybe some smectite or other clay minerals. And while all other rare earth, rock hosting minerals are being removed, like quartz and all the feldspars and mica, they're removed and turning into clay minerals. In the end, what's being left is just the clay minerals, but the rare earth, they stay there. So by removing all the constituents and all the other minerals and effectively keeping the rare earth, it leads to an upgrade by depletion of the rare earth to up to 5 times. So then the grade of those deposits would be around 1,000 to 2,000 ppm TRL. That's what we see in those drill intervals and also in the deposits. Overall, on a global scale, they're a source of heavy rare earth, including terbium and dysprosium. Those are the 2 ones you need for permanent magnets, especially for high temperature applications. And that's also the advantage of clay-hosted rare earth deposits over, let's say, carbonatites or heavy mineral sands. But they would be other rare earth mineral sources, and they don't have the heavy ones to that extent. Now, what this talk will be quite about is about the deportment of rare earth. And they are either in primary mineral form. There would be an example here, that would be monazite, and that would require a lot of acid to break it down. That's just an example here of the H+ moving in and how it would displace the rare earth. So it needs a lot of acid, so not overly economic in clay-hosted deposits. The second deportment type would be that rare earth precipitated secondary rare earth minerals. Once primary minerals decompose, and then you would form something like, for example, here, rhabdophate and a hydrous rare earth phosphate. And they still require a moderate amount of acid to break them down. You see they have a higher surface area already, but still need quite a bit of acid. And what's the ideal scenario is that what everyone's after. They want that ionic component to be quite high. So that would be the ionic mineralization, where you just have the rare earth loosely adsorbed on the surface of the clay minerals. So it would be a kaolinite here. And you see rare earth 3+ sitting here, it's adsorbed onto the surface of kaolinite. And then you can remove that with ammonium cations. So 3 of them would eventually displace the rare earth 3+, and off it goes into solution. So that's the preferred way that you want it to be. That means you don't need any additional acid for the extraction. And deciphering the rare earth deportment is quite crucial to decide on the processing strategies in the end. Now let's have a look into mining and projects globally. In the top right, you can see a map here of a lot of rare earth projects and regions where there's a lot of projects and also mines. So you can see a lot of activity here in Brazil. There are a lot of, they also covered quite a few companies that are listed on the ASX that publish their data. And it looks quite promising for some of them. There are a lot of projects that have been going for a long time in Africa. For example, the Makutu project in Uganda. And I'll talk mostly about the projects here in Australia today. mining only really takes place in southern China and also in Myanmar, here in Kachin State, for example, next to Yunnan. It used the dominant rare earth mining technique used to be strip mining, but now it's changed into in situ mining. So there's a schematic here on the bottom left. You can see those injection wells where ammonium sulfate solutions are being pumped into the ground, and then they percolate here through the area and absorb the rare earth from the clay minerals. Eventually, they will there will be an area just above the basement where the solution's accumulating, and then it will trickle down to the side, to the flank of the hills, and that's where those evaporation pools and tanks are that collect those ionic solutions with the rare earth in them. Now, this actually sounds quite simple when I explain it that way, but if you look into it, how it looks in Google Satellite, it's a bit of a mess, actually. So you can see the border here between China and Myanmar, and that would be the Kachin State, and you can see a lot of logging that happened here in the area, and there's all that logging that has happened means that this infrastructure that's being put in place for in situ clay-hosted rare earth mining. And you see in a couple of those areas here, for example, and here, those would be those evaporation pools. So if you zoom a bit further in, that's how it normally looks. So overall, not the nicest of processing techniques. Now, we've seen a lot of exploration activity then in Perth, and also seen a lot of issues by talking to a number of companies and our clients. And what we figured out then was the deportment of rare earth overall is not well understood, which leads to extraction issues. So you don't know whether you need to use ionic solutions, whether you need a bit of acid like HCl or sulfuric acid, or maybe even organic acid like citric acid, for example. Then the Australian deposits were quite often compared to the ones in southern China, but we would argue that there are quite a few differences, and we'll have a slide about that at the end of the talk. Overall, there's not too much geological knowledge about the rare earth behavior in the surface environments, and also there's been a lot of different matrices being published on the ASX about the rare earth grade and leaching techniques. For example, different analytical techniques have been used, like for acid digest or fusion or weak acid digest, and different leach tests have been done, and all these weird acronyms that have been floated around. So there's overall a lot of confusion in the market, and it was quite difficult for any investor to see what defines the viability of the project. So we've spoken to a lot of companies and asked which question they have, and then we went to Mariva and asked them if we can carry out a characterization project. And because we have an SEM and some smart people in our team, so we thought, why not? And sure enough, we did get the project with Mariva about characterization of clay-hosted rare earth element deposits in Western Australia. And those would be our industry sponsors. That would be Voltaic, Dreadnought, Terrain Minerals, MTM, AR3, Golden Mile, Auric Mining, HRE, and Mount Ridley Mines. And they've all provided a lot of samples to us. And then we've done a lot of analysis techniques like XRD, different analytical lab techniques with ALS, and also dissolution tests with ANSTO. All right, let's have a look now at a review that we've done across all clay-hosted rare earth projects in Australia. So you can see that map here on the left-hand side. All those dots means that there are some clay-hosted rare earth projects that have been published. You can see the majority of them are actually in the Yilgarn Craton. Then there's quite a few here in the Albany-Fraser orogeny. That's quite often called the Esperance region by all the clay players. We see a lot of activity also in the Gawler Craton, and more recent activity as well in the Delamerian orogeny, and also up here in northeast Queensland. Overall, it's 89 projects, and they're all run by junior exploration companies. Now, if we move one step further, all projects that already have an established resource, that would be 14 at the moment that have been published. And on the right-hand side, you can see, again, the same map, but this time only the ones that have a inferred or indicated or measured mineral resource. And you see the tonnage in million tons, so depending on the size of those circles. And also the total rare earth oxide grade ranging from white to a dark red. But before I get into that table, maybe let's talk a bit about the rare earth first. I'll go back to that slide in a second. So rare earth are normally split into the light rare earth and the heavy rare earth elements. There's no defined cutoff, I guess, between lights and heavies, but that's what the market's typically using, a cutoff between samarium and europium. But what's quite important is that the money is sitting in those four that have those dashed boxes around them. So praseodymium, neodymium, terbium, dysprosium. And they're often called the MREEs or MREOs. That would be the magnetic rare earth oxides. So all those ones are being used in permanent magnets. And they make some effect that we've learned at the Rare Earth Conference in Canberra last year. They make up over 90% of the rare earth market in general. So whenever companies put up their percentage or their concentration of MREs, that's actually what's the sellable product in the end in a mixed rare earth carbonate that a company will eventually sell. So the economics sit in those four. And the rare earth prices overall, they differ quite widely. So if you look at cerium, it's just $1 per kilogram. Excuse me that I've used some of the German charts here, but I think the German Geological Survey does a pretty good job in putting those graphs out every month. So they update them quite nicely. And here you see cerium, praseodymium, neodymium, terbium, and dysprosium over a range of 2 years from March 2022 to March 2024. And you can see cerium is just sitting at around $1 per US dollar per kilogram. So there's quite a lot of cerium that's being mined from mineral sands and also from carbonatites. So given the low grades that those clay-hosted rare earth deposits have, it's considered a waste product, so you can't really sell it on. But then the money is made, especially here in terbium, dysprosium. If you look at terbium, it used to be quite valuable. Now it's sitting still around 1,000 US dollar per kilogram, so there's quite a difference. So rare earth are not all equal. But then what you can also see here, there's quite a bit of a decline here. Yeah, the highest prices that we've seen were in February and March 2022. Then at that point in time, neodymium was around 180 US dollar per kilogram, and now it's down to 60 or 50 maybe US dollar per kilogram. So that's looking not too good at the moment for the market, but what comes down must come up, right? So I'm hoping to see some uplift here in the future. All right, now with that in mind, we know a bit more about what those terms here mean and what they're used for. So, but let's look at the tonnage first, maybe about those 14 projects. They're roughly around 190 million tons. That would be the average grade. There's some that are a bit smaller that can grow when the company keeps on drilling a bit more. Some are quite large, for example, one from OD6 here, 354 million tons. The total rare earth oxide grade is just below 1000 ppm on average, but some you can see are a bit higher, some are below that. And then a metric that's being published by most companies, not all, but most of them put it out there, is the proportion of their magnetic rare earth oxides. Again, those four candidates we've talked about before. And some have quite appreciable amounts. So for example, Rubble Mount here, or Covalinia, or also down here, the Barclay project. So those heavier magnetic rare earth, dysprosium, terbium, also quite important to see how much is in there. You can see now we're down to a lower ppm range here, 36, and maybe that's on here, 31. Those are some of the better ones. But even in carbonatites, those two elements are normally in a lower ppm range. So overall, they're quite low in general. The resource cutoff, we've talked about it before briefly. Cerium is a waste product, so you need to remove it from almost commonly at least remove it from the total rare earth oxide. So you have a cutoff and remove the most abundant rare earth with it. So you get a bit closer to the economics of what's in there. And the cutoff, which would mean the lowest amount of rare earth that's incorporated into the resource, that's normally sitting on 300 to 400 ppm TREO minus cerium oxide. The underlying source lithology, you can see it's mostly granite across the board, but there's also a couple of deposits over Australia where you have mafics and even ultramafics. Most commonly, it's mafic basalt that's also as an underlying source rock. The date published, you can see the majority of them come from 2023. Some companies regularly update their deposits, their resource estimations as they keep on drilling. There's two actually that have been released this year. As you can see here, the maiden resource as well here from the Atria deposit. And the first one was the Krakatoa in 2022. And that sort of correlates with the rare earth price that we've seen that had a peak in March and February 2022, and then companies went out there and drilled, and then it takes maybe a year to come up with a mineral resource estimate after that. But still, you can see there's companies that are still putting them out, and there are still more companies with resources coming up in the pipeline. So there's still a relatively active field. So the underlying lithology now. I'll talk a bit now about the mineralogy in general about those deposits, and start with the underlying lithology, and then over the next few slides we move a bit up in the regolith profile. So what we mostly see, we've had it before, is granite gneiss. That's what everyone knows from the Gilgan Craton, for example. A lot of basalt and also some ultramafics. There are some fancy ones like quartzite and limestone, especially in South Australia. And there's been a brilliant paper by Stefan Löhr from the Uni of Adelaide and others about the Coppermura project. And they've shown that there were granites in the hinterland, and due to in the drainage pattern, they've been mobilized and eventually precipitated on top of limestone. So the limestone did not add any rare earth to the system. So they also come from a source granite. But that's why sometimes you have some of the more fancy lithology. So it takes a bit of effort to figure out. Most of the rare earth deposits are from in situ weathering profiles, but some of them also transported. Now let's look here at the images at the bottom. That's one example of a monster granite that was identified as a potential source rock. This one, for example, just a case study to show here, had those brown patches, and we didn't know at first what they represented. And then we looked, that's an image from a thin section here, a backscale electron image. We zoomed a bit further in and we found those patches again, and they were a mixture of allanite and its weathering products, and as well as magnetite and biotite. So they formed these brown patches here. And then we've ran automated mineralogy on the whole slide with our system here, with our SEM. And we've seen a number of potential rare earth element host source minerals in here. That would be allanite, apatite, epidote, titanite, and zircon. And I'll talk a bit about them over the next two slides as well. So again, primary source minerals. Most of those samples here, they come from seprock, because companies normally drill with an air core drill rig. That means they drill easily through the clay horizon, but then plate refusal is normally just above seprock. So we don't really get any fresh samples from those deposits, but at least we get an indication of what's down there, what was the original rare earth source that's in the ground. So number one here would be monazite. That's always the most common one we see across all projects. And it's predominantly a light rare earth element phosphate. You can see representative EDS analysis that we've done with our SEM. So you can see all those numbers here. They just show some representative spot analysis. So monazite quite prominent here with light rare earth elements. Something we've seen in 3 deposits was bastnasite. And bastnasite, while it's still a light rare earth mineral, it contains quite a bit of the heavies as well, especially when it's occurring in more of the mafic source rocks. That's something we've seen in 2 or 3 deposits where there was an enrichment in the heavies. That was quite unusual for us to see. Then everyone's favorite, xenotime, because it's a lot of companies are targeting this mineral because it is a heavy rare earth phosphate, so it contains more of the valuable heavy rare earths. For example, as well here, dysprosium with 4% from that mineral. Then there are also minerals that are not rare earth minerals sensu stricto, but they contain minor components of rare earth. That would be, for example, apatite and zircon. So you see that nice outline here of that apatite grain. There's a bit more apatite over here. And you can see it has this darker core and a brighter rim. And that brighter rim actually correlated with rare earth enrichment. And that's the EDS analysis from that bit. So you can see there's more than 2% of rare earth that we found in here. So when apatite breaks down, it also releases rare earth to the clay horizon. And then we see zircon here. Every now and then when we shoot a zircon, we get a nice yttrium peak. That means there is some enrichment of heavies in some of the zircons as well. Allanite is the rare earth mineral that breaks down the easiest from all, quite a complex mineral. And I'll talk a bit about that image on the next slide in more detail. And titanite is another calcium titanium silicate, but it has also some amount of rare earth in it. You see that's a nice little pseudomorphic replacement of that titanite grain. Here there's still a bit of a relic left. You see the outline is quite nicely preserved, and now it's just rutile, or just call it here titanium oxide, that's left. And there, if you shoot that one, there are no rare earth left in it. So all those minerals can release rare earth to the clay horizon when they break down. So just said we've have a look again at that allanite grain. So you can see it here. just disregard the pores here. That's just resin. It probably happened during sample preparation. And you can see it's sort of eaten up by this layer of iron oxide. That's also quite prominent. If you look at the iron map here, you can see it's lighting up here. So there was a layer of limonite that we've seen around the ilmenite. And then there was this bright rim around here that we've seen. It was a mixture of mostly secondary ilmenite, but also cerium oxide. And we got the odd fluorine peak every now and then. So there must be some rare fluorocarbonates as well in that mineral. And something we've also seen all those lines along the cleavage planes of albite, but also along through cracks within albite. And if you look at the rare earth maps here, for example, I've plotted here lanthanum and neodymium, you see the exact same complex mineralogy we see on the rim is also what we get here within those cleavage planes and fractures. So that's the way how the rare earths sort of escape from the ilmenite and hopefully end up in the clay horizon at some point. And you see overall how manganese tries to escape during weathering, the rare earth try to escape, and also iron as branching out from that ilmenite mineral. Now let's have a quick look at the normal rock forming minerals, how they decompose overall. So not disregarding the rare earth minerals for a second. You see that's a photo from saprock. Quartz is still relatively intact, but you see a feldspar that's has some history behind it. So you see all those dissolution pits here along the cleavage planes, also along those planes and along that orientation. So it's starting to decompose quite a bit and then turning into kaolinite. If you move a bit up in the regolith profile into saprolite, you can see all the feldspar has been decomposed already to kaolinite. And then that's the moment also when we see that biotite starts to exfoliate and decompose, and it's shedding out all the potassium and iron and magnesium, and what you're left with is just aluminum and silica and oxygen. And that would be your kaolinite that you have in the end. And that's the only 3D image I'm going to present today from a secondary electron image. You can see all those nice little booklets here of kaolinite and here as well. And there's a couple of those booklets everywhere. And at the same time, you see those needles. There's here one, for example, there's another one here, and they're everywhere. That whole cluster here is full of needles. And if you would zoom a bit further in, then you would see that those needles are actually halloysite nanotubes, but you really need a high resolution SEM to resolve that. But we were quite happy with the image that we got from here. And you can see that there's a lot of space between the interlayers here of kaolinite. So there's a lot of surface area, and that's where you want to see all the rare earth being absorbed into those layers. Now let's move a bit further up into the saprolite, and what we see there quite often are relict phases of the primary granite. So those are minerals that have not been weathered completely, that are still sort of intact within the regolith profile, and they contribute to the rare earth budget in the end. So we can start here with monazite, again, the most abundant one we see, and you see it's nicely hosted here in clay. It's starting to decompose. You see those pits everywhere here, and you see a bit of free precipitation going on here. I'll talk about that as well on one of the next few slides. There's two examples here of bastnasite. So still quite intact here that bit, but overall you can see the grain as a whole has seen quite some history and has experienced a lot of dissolution. So has released a lot of the rare earth to the clay horizon. That would be another example of bastnasite. The whole grain used to be probably one aggregate of bastnasite minerals, or bastnasite crystals. There's still some left at the middle, but overall you can see this funny hair-like growth that's branching out of it in all directions, and that would be the secondary bastnasite that we see that's precipitated here. So while some of the rare earth are being released, some others are actually retained. So it's a 50-50 situation, I guess, here for that bastnasite. Zircon we also see quite regularly within the clay profile. I guess everyone knows how reliable, how robust zircon is. Doesn't really like to decompose, but if you're in a clay horizon in the plasmic zone, eventually it also starts to decompose to some extent. And cinotime we can also see here that's seen some weathering as well, but overall it's still quite an intact form within that clay bit. And one mineral that's probably the most robust one that doesn't really like to decompose was fergusonite, a rare earth yttrium, rare earth niobium oxide. But that was just a mineral that we've just seen, I think, in one deposit only. All right, the other department of rare earth then would be the secondary rare earth minerals. So they form when the primary rare earth minerals decompose. That's when secondary ones can form. And the most dominant one we see are secondary rare earth phosphates. Now I've called them all rhabdophane here for simplicity, but I'm not sure how hydrous they actually are, if they are secondary monocyte, actually rhabdophane, but let's call them rhabdophane for simplicity, because that's normally the stable form of rare earth phosphates in the low temperature environment. So if you start here with that image, you can see how rutile is decomposing completely, and then rhabdophane takes up the space here in the voids, as well as you see all those dissolution along the cleavage plane of rutile, and then as soon as it dissolves, rhabdophane takes up the space here. And kaolinite, you can see a lot of kaolinite here. That's probably also from a decomposing biotite that forms this book texture. And as soon as that exfoliation happens, you see that rhabdophane takes up the space. Another example would be here that you have the deep pyramidical shape that I've outlined here with a dashed line. It could have been maybe the outline of a former apatite, or maybe an outline of a former monocyte that likes to have that crystal shape. And that's been completely replaced by secondary rare earth phosphates. There's a lot of porosity in here, and also a lot of rhabdophane that's floating around that mineral. And some of the cavities here have also been filled by an APS mineral. There would be an aluminum phosphate sulfate group mineral. And an example here would be fluorensite, for example. But there's a lot of variability. There's countless of APS minerals, and there's probably still more to be found. One oddity that we've seen in 2 projects, and it was quite prominent in this one. So sample D and image D and E come from the same project and from the same resin block that we've analyzed. And we've done an EDS spot here. First, we thought, okay, this may even look like it's still primary monocyte, but then we've done an EDS spot on here, and that's the spectra that we got. You see all the rare earth are in here, but no cerium. And you may remember cerium is the most abundant rare earth. So you normally see a massive peak where cerium L alpha comes in, but then there was nothing here apart from maybe this tiny little tip. And the EDS said, okay, there's no cerium in here. It was below the detection limit. And at the same time, we see that cerianite was forming in the same resin block. So that means, so that's cerium oxide, sorry. And cerium, you have to know, is the only rare earth mineral that has an oxidation state of 4+. So under highly oxidizing conditions, cerium does not like to partition then into some of the phosphate phase. It rather likes to form as an oxide phase here. So that's also, as far as I know, the only rare earth oxide that exists as a mineral approved by the IMA. That's actually good news if you form cerianite for the Explorer, because as we know, cerium is a waste product and cerianite is quite insoluble. So if the company does their leach test, they would not get any cerium in solution. And another example would be here from that we see in 4 deposits. And one deposit was quite dominant in those APS minerals that form these atoll-like growth. And yeah, those are the fancy ones that have quite a variable composition. Maybe quickly coming back to the rhabdophane. So rare earth and phosphate, they don't really like to be in solution together. So whenever apatite dissolves or monocyte dissolves or another rare earth mineral dissolves next to apatite, and you bring them both into solution, then secondary rare earth phosphates precipitate. That's a quote I quite like. It's phosphate is a depositional ligand rather than the transport ligand of rare earth. So that's why we see a lot of rhabdophane, or at least secondary rare earth phosphates within those deposits. That's a bit of a schematic. Again, coming back to our favorite minerals, monocyte and rhabdophane. You see how it starts here in the regolith in the lower profile, maybe in saprock. Monocyte still looks relatively intact, maybe seen a bit of weathering here on that bit, but overall still happy. And then if we move further up in the regolith profile, we see how there's a lot of kaolin already around it. And you see that the outline is still relatively preserved, but there's been a lot of dissolution going on here. And if you zoom a bit further in, you can see all this needle-like growth here. So that's characteristic of rhabdophane that's forming. So then this part here would be the secondary rare earth mineral phase, and that would be the relic primary one. So you see both rare earth deportments in one image here. And if the process is complete, that's a texture we see quite regularly in those deposits, is that you just have that outline preserved of what used to be a monocyte grain. And now you still have that needle acicular-like growth that's left here. So that's all rhabdophane. Now the monocyte is gone completely. But what you can also note is that there's a lot of porosity. So you could argue that maybe 20% of the rare earth have been trapped in situ, but then 80% of the rare earth would have moved into the regolith profile and eventually form ionic mineralization. And that would be the third type of deportment that I want to talk about. That's the ionic leach test. And overall the ionic portion, so what percentage is actually adsorbed on the clay surface. So you see, that's what companies normally do. They go to service providers like metallurgical labs. There's a lot here in Perth, for example, but also Ansto gets a lot of traffic. And what those companies normally do is they use a sample and put them in a solution of ammonium sulfate. They do that test at ambient conditions, so that means 20 degrees and also no pressure involved. They try to maintain the pH at 4. The solid density is 2 to 4%. That means you, in a drum roll, for example, you put 2% clay in, and the other 98% would be your ammonium sulfate solution. And the test runs from sometimes 30 minutes up to 6, 7, 8 hours. But on the downside, the typical extraction rate that companies are getting is just 0 to 10%. So not overall, not that high. And that's what's been published on ASX. On the ASX overall, our leach tests are still pending for the MREVA project, so I can't even make a comment on that. But that's overall the number we see quite regularly, 0 to 10%. If you compare that to the deposits in China, there was a brilliant paper by Li et al. In 2017. And he put some numbers out for a few deposits that he reviewed, and then got the ionic proportion of maybe 40 to 60%. So also not 100%, not 80%. It's also in the mid-range, I guess. But that's something you can expect from the world-class deposits. But they also note here that there's quite a few deposits that have dominantly secondary phosphates instead of adsorption kaolin. So I guess in that sense, it's quite similar to the rare earth deposits in Australia. There are a few examples here from South Australia, Queensland, Tasmania, mostly of isolated samples that they've done test work on that got some better extraction rates for those 4 favorite candidates, and those are the conditions here. So some companies do get good recoveries every now and then. If they don't, if they have the 0 to 10% extraction rate, a lot of companies either keep the same conditions and then they just drop the pH to 1 to 2 using hydrochloric acid or sulfuric acid. Or they just scrap the ionic leach test altogether and just use a lot of acid and also extract the rare earth from it. So they use between 10 to 100 grams per liter of HCl. A lot of companies are now using around 25 grams per liter. And that often gives recoveries of sometimes even up to 100%. But then it's always the question, how much iron, how much aluminum, how much silicon do you also get into solutions? That would be your gang that you don't actually want to be in solution. So in the beginning, I've promised a slide on the mineral system, and the mineral system of southern China may not apply to Australia. And there were 2 pretty good papers that defined sort of the mineral system, maybe not on purpose, but at least they've laid the foundation for it, in my opinion. They were Bao and Zhao in 2008 and Li et al. 2017. But there's also many other brilliant papers that we've published on nucleoside rare earth deposits, but I've just put those 2 out here, and I've listed some of the factors they've used. So it would be the exogenic and endogenic factors they published. So exogenic would just be all your surface processes, like overall climate or weathering processes, rainfall, and endogenic, that would be more of the geological factors like tectonic forces. And if we compare them here with a case study between South China and I've used the example of the Yilgarn Craton to be a bit more consistent. If we start with the bedrock, that's actually quite similar. So we have granite and volcanic tuffs, and in the Yilgarn Craton, it's mostly granite and some mafic rocks. So that's relatively similar. Where it starts to differ is, I guess, with the age. They're quite young in China. They're all Jurassic to early Cretaceous. And what we have in the Yilgarn Craton is all essentially Archean. The host, something we've talked a bit about maybe in the beginning, in South China, they have maybe a bit more simple regolith profile with the A, B, C horizon, just the Ulmic horizon up here. And then between the B and C horizons where the rare earth are normally adsorbed. And there may be a bit more complexity in the regolith here in Australia with ferricrete and duric crust and calcrete and mottled zone and whatnot. Something I know quite very little about, but there's probably a lot of people in this talk that know quite a bit about this. So overall, it may be a bit more complexity in the host zone, but predominantly the rare earth are hosted in the plasmic zone. Topography is quite different as well. So you have undulating to moderate steep forest terrain in South China, and that helps with the weathering process as well. So you can see there's some gravitational force that helps to move the rare earth further down, and then they can accumulate a bit further on slope of the hills. But that would not be the case, I guess, in the Yilgarn Craton, where you just have flat bushland. So there's no gravitational help with regards to weathering. Salinity levels is another difference that is noticeable. I've reviewed a few papers I just read through a lot of papers of Chinese clear-acid rare earth deposits, and some of them actually put out numbers on the salinity levels, or at least of the levels of some wells in the area, and they're normally around 20 or 10 to 20 to 30 ppm chloride. But I've also seen one map of the hydrogeology of the whole country and the southern parts in particular, and then that was all falling into that range below 6 or 7 ppm chloride. And if we now compare that to the Yilgarn Craton, different level here, we're talking about salinity levels, not just chloride levels, but you see they can be quite high, especially south here of that magic Menzies line. And there would be around 1.5 or 1.4 to 3.5% salinity, and even higher in some of those paleochannels. So that may not help with the ionic proportion of the rare earth deposits, because chloride is a prime ligand to transport the rare earth away. The geodynamic setting is also quite different. In southern China, you have uplift and denudation sort of in check. So while tectonic forces bring those hills up, at the same time, you have erosion happening. So all this tectonic uplift helps with ongoing and speeding up the weathering process. And I would argue that's not necessarily the case in WA, where you have at the moment more or less tectonic quiescence. The timing of weathering, so that feeds into what I've said before, it's an ongoing process in South China. And something also don't know too much about. There's probably a lot of people again here in this call who know a lot about that, when weathering predominantly happened in the Yilgarn Craton, for example. But in papers from Anand, Ravi Anand, and others, you can see, especially here during the Mesozoic, there's been a lot of rainfall in the Middle Eocene, for example. And right now, there's not too much rainfall happening. So now we're down to 250 millimeters per year compared to what we have in southern China. So overall, this means weathering is ongoing, and maybe weathering process is quite slow in the Yilgarn Craton. But you may also argue that what we see currently in the Yilgarn Craton may be a process that has happened in the Middle Eocene here. And if you see a sort of a fossilized process of what has happened back then there may be ionic mineralization out there. So now to come to the summary slide here. Overall, we see very active exploration across Australia. Slowed a bit down over the last half year, certainly, but still we see more companies coming out with their projects. The main regions we see are the Yilgarn Craton and the Esperance region. It's listed here all the primary magmatic source minerals and all the secondary rare earth minerals that we see quite often in those deposits, predominantly rhabdophane. And I guess the main take home would be the deportment of rare earth, that you can have the rare earth in ionically adsorbed form. That's what you want. You can have the mineralic primary rare earth mineral phase, so minerals that survived from this underlying source granite, or they can be as a secondary rare earth mineral. And that all feeds into the TREO value that the company put out when they have their drill results or resource estimations. So I would argue it's crucial to identify the proportion of those three deportment types to guide metallurgical work. And that's something we also want to keep working on with Mariva for a potential stage 2 project. All right, that's it for me. Hope there will be some questions.